Hello everybody, my name's Charles Day. I'm the Editor-in-Chief of Physics Today magazine, and I'm delighted to introduce today's webinar on the subject of advanced microwave topics for quantum physicists. This is a field I first wrote about in 2006, and I'm now delighted to see that it's become the basis of a thriving industrial sector. So our speaker is Mark Euler from Tabor Electronics, and take it away, Mark.
Thank you, Charles, and welcome everybody to the seminar. First of all, my degree is in solid-state electronics, and then I specialized in microwave test equipment for 30 years, so I feel I live somewhere in between the physics and microwave engineering worlds. I've taken some time to choose some appropriate topics. I'll hope you find value in the content, and we can consider a lot of these topics as an introduction. If you want to deeper dive, please feel free to contact us. We'll have all our names, contact details at the end of the presentation. Now, on to the topics. The following topics represent the key elements I've chosen for understanding signal behavior at RF and microwave frequencies. We will begin with the fundamentals of wave propagation, understand the difference in wave velocities through a vacuum versus cables of different types and different lengths. Then we'll go on to look at impedance and why is that important. Gain an understanding of impedance matching and transmission line theory to ensure maximum power is transferred between two devices. The second section deals with passive frequency translation and how the properties of nonlinear devices, namely diodes, can be configured as frequency multipliers or frequency summation devices such as mixers. We'll compare several mixers' performance and understand what trade-offs to compare when choosing an appropriate mixer. Synthesis uses many of the same principles as frequency translation, and in this section we'll detail how to convert a reference frequency to a desired frequency. And remember, there's two types of synthesis technique, direct and indirect, and signal generators usually combine one of these techniques or both these techniques to produce a desired signal of the adequate spectral purity that we require. Modulation is the process of encoding information onto the frequencies that we've just generated through synthesis, and we're going to specifically look at AM and phase modulation in this presentation and how they're combined to create vector modulation. We'll look at both analog and digital implementations of vector modulation. Frequency planning is the optimization of the frequency translation path to ensure that the intermodulation, harmonics signals, and any other signals don't interfere with the desired spectral purity of the signal that we're trying to create. And then the final section is signal analysis. And many of the fundamentals of signal generation equally apply, and we'll look at different analysis techniques and examine the benefits and trade-offs of each one. Let's take a look at wave velocity. An electromagnetic wave such as an RF or microwave signal propagates through a vacuum at approximately 300 million meters per second. However, through a coaxial cable, this will vary depending on the type of cable. There are multiple types of RF cable, and I've shown two on this slide. We'll look at the detailed specifications later, but for now it's important to realize that the velocity of the signal is reduced significantly compared to that of a vacuum. In most of the experiments in this webinar, I've used an RG316 cable. And this has a velocity factor of 0.7, which means my wave is going to propagate through the cable at 70% of the speed of light. So why is this important? If my cable is half a meter in length, or 0.53 to be exact in this example, and we know the velocity factor is 0.7, then it'll take 1 over the speed of light times the velocity factor to travel 1 meter, which takes around 5 nanoseconds. Our cable is 0.53 meters in length, so the time it takes, calculated and measured on the oscilloscope in this example, is around 2.5 nanoseconds. You can see the time delay can represent a significant phase shift in the signals. So if the relative phase of two signals traveling along two cables needs to be minimal, then the cable needs to be electrically phase matched, or we must employ another method such as extending the length of one cable until the delays are equal. When connecting two or more RF or microwave signal devices together, it is important to standardize on the RF connection. RF systems usually define a connectivity impedance of 50 ohms. There's nothing special about this value, but matching the impedance is key, and I'll explain more about that in the upcoming slides. But for now, let's connect our arbitrary waveform generator to an oscilloscope. In this drawing, we have a non-inverted output connected to channel 2 and channel 3 in parallel, as shown by the coaxial T connector in the picture and by the lower schematic. The inverted output of the ARB is directly connected to channel 4. The direct connection on channel 4 has a measurement result of 1 volt peak to peak. This is what the arbitrary waveform generator is set to. If there was no source and load impedance, then the voltage would be 2 volts. However, the 50 ohm standard essentially creates a voltage divider network of the 50 ohm source impedance and the 50 ohm load impedance. And hence we can say when the AWG is set to 1 volt peak to peak, we will measure 1 volt peak to peak across our 50 ohm load. In the second example, we have the 50 ohm impedance of each channel in parallel due to the coaxial T connector, thus creating an overall combined loading impedance of 25 ohms. And our measured value, as expected, is 0.5 volts peak to peak. It is sometimes useful, like in this case, to draw out the schematic of the interconnects to understand why the voltage of the signal is not what you expected. Now we understand velocity and impedance. Let's look at the transmission line properties of the cable. Our cable is essentially made up of groups of inductive and capacitive elements, and our wave propagates through each element, as we learned earlier, with a certain time constant, summing up to our velocity factor over a meter. And as we learned on the previous slide, if our impedances are all equal, the wave propagates through the system as expected, and maximum power is transferred. But what if we do not have a matched impedance system? If our load impedance is not matched to the source impedance, then this mismatch will cause the wave to be reflected back on itself through the transmission line, to a point where the addition of the transmit versus reflective waves creates a summation or superposition that looks like a stationary or standing wave. This can be demonstrated on my oscilloscope by setting the input impedance of channel 3 to 1 megaohm. If I sweep the source from a frequency of 100 megahertz to 1200 megahertz, with the persistence on the oscilloscope set to on, you can see the incident and reflected waves summing at different amplitudes depending on the frequency. This is visualized in the center plot. The bottom 3 plots visualize summation over a meter of cable, measured at 0.5 meters and the 1 meter mismatch point. At 75 megahertz, or a wavelength of 4 meters, the voltage at 1 meter is maximized and is much higher than the expected 1 volt peak to peak. And at 0.5 meters, it is minimal. At 300 megahertz, or a wavelength of 1 meter, the amplitude at each measurement point is equal. At 1200 megahertz, or 0.5 meters of wavelength, the signal at 1 meter is completely cancelled, while at 0.5 meters, it is again at a maximum, which is much higher than the expected 1 volt peak to peak. The superposition of waves due to the mismatch impedances can seriously affect maximum power transfer, and keeping the system's impedance matched is critical. Finally, as our transmission line is, as we previously discussed, inductive and capacitive elements, the closer the signal is to DC, the inductors are going to conduct more. The higher signal frequency is, the capacitors are going to conduct more, or vice versa. This means there is an associated frequency response of the cable. I used my spectrum analyzer with tracking generator to sweep the cable and verified the loss at different frequencies, and verified that the measurement matched that of the datasheet. In summary to this section, an RG316 cable is specified by its impedance for maximum power transfer, its capacitance and signal loss representing its frequency response over its length, and its velocity of propagation and delay specification telling us how fast our wave propagates through it. Now we've spent some time addressing the fundamentals of wave behavior, let's examine the phenomena of frequency translation using nonlinear devices. A nonlinear device follows Ohm's law. If the resistance remains constant, a change in voltage across it will proportionally change the current flowing through it. A semiconductor device, such as a diode, is nonlinear. It does not conduct or conducts very little until a voltage drop across it exceeds a certain value. Then it begins to conduct. The two red plots show the difference. As an example, I placed a sine wave across a diode. The upper blue waveform on the right-hand plot is the arbitrary waveform generator output, and the lower green waveform on the upper plot is the voltage across the diode. As you can see, it only conducts after the switching voltage has been exceeded and the negative swing of our input signal does not cause current to flow. The lower plot, yellow trace, shows the frequency response of the voltage across the diode. The spectrum contains the fundamental frequency and then integer multiples of 2x, 3x, etc. We would pick one of these multiples as our new frequency and filter it appropriately. Also, it's worth mentioning about the drive power. The diode switch on, or third switch on point, or its point where it conducts is 0.7 volts, which equates roughly to 1 dBm of power. In a real mixer, we'll need to put in much more power than 1 dBm, typically between 10 and 15 dBms for most commercial mixers. Commercial multipliers and mixers have more complex designs and are usually based on diode bridges, filter circuits, and in the case of mixers, transformers are used to cancel the LO and IF feed-through frequencies. On the left-hand side of the slide, you can see I've set up a multiplier, and this one is optimized for 2x multiplication. If you now look at the right-hand side of the slide, we can examine how a mixer works. When an LO is applied, the positive swing turns on the green half of the bridge, and the negative swing turns on the yellow half of the bridge, thus only allowing the input frequency current to flow during these on and off times. If the LO frequency is much greater than the IF, which is usually the case, the high-frequency switching of the diode circuit produces a time domain envelope of the lower frequency, or effectively adding the LO and the IF together. Using transformers on the input gives us a balanced design. A single balanced mixer, which is less common, suppresses either the local oscillator or the signal input at the output, but not both. While a double balanced mixer, the most common type of commercial mixer, has both its inputs applied to differential circuits, so neither of the input signals and only the product signal appears at the output. However, a double balanced mixer, as shown in the diagram, does require usually a higher drive power than a single balanced mixer. As I mentioned in the previous slide, drive power is important. Too much and you'll increase the intermodulation products of the mixer. Too little and the mixer will not function correctly, as it will be operating in the lower parts of the IV curve we looked at on the last slide. Let's look at 4 different types of mixer: a mini circuits, analog devices, formerly Hittite, and quantum microwave mixers, all of which are double balanced mixers, but they've been optimized for various performance criteria. For example, the mini circuits mixer has a wide IF range. The analog devices mixer has been optimized to suppress even products, and the quantum microwave mixer has a narrow IF band, but has been designed to optimize, in this case, the lower sideband and suppress the LO and upper sideband. Quantum microwave products are also designed to work at low temperatures, typically used in physics applications. All the tests I perform are at 7 GHz. The LO is provided by the Tabor lucid signal generator and the IF a Tabor Proteus 9082M 9 gigasample arbitrary waveform generator. I've also included the 4th type of mixer in this comparison, and this is built into the DAC of the Tabor Proteus 9082. The LO is provided by an inbuilt numerically controlled oscillator, and the whole process of mixing is implemented digitally. However, the maximum output frequency I can achieve in this last case is 3.6 GHz. Comparing all the mixers. The mini circuits mixer shows the first sideband, the second sideband, and the third sideband. It takes about 10 dBm of power. It's got a wide bandwidth of 4 GHz. The ADI requires the largest power at 15 dBm from the spec sheet, and it effectively suppresses the even products, and the carrier feed-through is attenuated by 28 dB, so it's a reasonably good performing mixer. The quantum microwave mixers are designed for low noise applications and therefore require a lower LO power, specified on the datasheet at 9 dBm. And you can see that the feed-through and the mixer products are well suppressed, and the lower sideband is almost 35 dBs higher than the LO. Finally, the digital implementation has no feed-through, and the unwanted sidebands are well suppressed. However, all the other mixers' operational frequencies are up to 12 or 15 gigahertz. The digital implementation is limited to 3.6 gigahertz and is related to the sample rate of the instrument. However, we will learn later how to use these devices in multiple Nyquist zones, plus through effective frequency planning, a combination of digital modulation and analog mixers will result in the best signal performance at the required frequency. We will now extend the concept of frequency translation to that of frequency synthesis. The dictionary definition of frequency synthesis is the ability to generate a range of frequencies from a single fixed time-based oscillator, or what we often refer to as a reference. There are multiple synthesis techniques that fall into the category of direct synthesis, with multiple implementations in both analog and digital designs, and indirect synthesis, which is usually an analog implementation. Let's look at the block diagrams of each synthesis technology. Here we show 4 types of synthesis techniques. Going around the slide in the anti-clockwise direction. Direct synthesis is everything we have already talked about with respect to frequency translation. It is a combination of analog multiplication, mixing, and filtering. When higher frequency resolutions are required, this design does get more complex and requires more stages. However, in terms of noise performance, frequency stability, and frequency switching speeds, this is the most superior synthesis technique. Next, the direct digital technique. A direct digital implementation stores a waveform in memory and then uses a counter. And you clock the counter through each memory location at different speeds to produce a relevant frequency. The next is arbitrary waveform generators. Again, they store a waveform in memory, but this arbitrary waveform memory can store a multitude of waveforms in the memory, and the user can index and play waveform memory combinations. Finally, in the top right-hand corner, we have the indirect synthesizer, which is based on a VCO phase lock loop architecture. The VCO can create a frequency based on a voltage level, and the accuracy of that signal is determined by the error between the phases of the reference frequency and the VCO frequency. A signal generator will combine different synthesis techniques to create a range of frequency bands. Each technique may give a better frequency range, better noise performance, higher spectral purity, and each comes with a specific trade-off. Direct digital synthesis, for example, can create signals with good phase noise and high frequency resolution, but the frequency band is often limited as the process tends to generate a lot of spurious signals. A direct synthesis approach gives you low noise and high frequency capability, with frequency resolution, cost, and size being the trade-off. A VCO-based synthesizer, the most popular type of synthesizer, will generate higher phase noise than a direct system. However, it is more compact and has a lower manufacturing cost. A signal generator such as the Tabor lucid signal generator uses multiple synthesis techniques to achieve the best combination of frequency range, spectral purity, noise performance, and cost. Another element to consider, especially when using direct synthesis with frequency multipliers, is the rule of thumb that for every time you double the frequency, you'll get a phase noise degradation of 6 dBs. Here I connected a doubler to my lucid signal generator and observed the phase noise difference between 1 GHz and 2 GHz. Although it is possible to measure phase noise on a spectrum analyzer, it requires a very narrow bandwidth and a slow seed speed. Then the measurement needs to be normalized to a 1 Hz bandwidth. However, visually you can see in these two 10 kHz band plots, the phase noise has increased between 1 and 2 GHz. If we now look at the single sideband phase noise measurement of the lucid signal generator, you can see several effects are in play. First, the measurements are relative to the carrier. That carrier would be to the left of the y-axis and is often excluded from this type of plot. The first phenomenon we observe is the phase noise performance decreases at higher frequency multipliers, as we previously discussed. And we can decipher the phase noise plot into terms of each element of the synthesis technique. Close to the carrier, the phase noise is usually related to the reference frequency and has a very steep slope. Then from around kilohertz to 100 megahertz, you see a plateau, based on the noise contribution of the VCO. Finally, as you move further away from the carrier, the broadband noise becomes the more dominant factor. The reference really defines the quality of synthesis we perform in our signal generator. Quality can be defined by frequency stability, short-term stability or phase noise we've discussed already, and then longer-term stability is defined by specs such as aging or frequency drift. If we look at the number of references available in the market, there are multiple with different price points and different performance characteristics. Some are built into the signal generator and are based on oven or temperature-controlled oscillation techniques, often referred to as OCXO and TCXO, O being oven and T being temperature. And we can also purchase external references that can be derived from a Cesian time base, for example, an atomic clock, or with an antenna system, we can derive a fairly stable reference from the GPS system. We've discussed phase noise already, and understand every time you double the frequency, the phase noise degrades. Frequency drift is defined by changes in temperature and the aging specification. So in this example, you can see when Lucy's is tuned to 3 GHz, it drifts by 375 Hz over a year. This is actually a factor of 10 improvement over similar signal generators. If you want to have a number of signal generators phase locked together with each other, you would share a single reference between multiple synthesizers or signal generators. Let's explore what it looks like on the next slide. In this scenario, we have a single reference being shared between 2 VCO/phase lock loop synthesizers. If we share a 10 MHz reference with 0.1 degree of phase drift at 10 MHz, this will produce a 10 degrees phase drift at 1 GHz. By changing the reference to 100 MHz, you get a 10x improvement. However, this will still cause significant frequency drift problems at higher frequencies. One way to compensate for this is to use a higher frequency reference, preferably in the gigahertz range. In order to demonstrate frequency stability over time, alongside some arbitrary room and rack temperature changes, I took a 4-channel lucid signal generator, set the frequency to 4 GHz, and with my oscilloscope set to maximum persistence, monitored the 2 locked sine waves for 15 hours. While not a quantitative measurement, qualitatively it does show there is minimum drift between the 2 channels over time and temperature at 4 GHz. So far, we've talked about how various types of synthesis techniques can be combined within a signal generator. The other element that determines a signal generator or defines a signal generator from a synthesizer is the output section. The output section of the signal generator provides us with the required amplitude. It allows for AM modulation, provides gain and attenuation, and ensures the absolute levels of the generated signals fall within a specified limit. The amplitude range is enabled using attenuators, and in the case of the lucid signal generator, allows a signal range of plus 15 dBm all the way down to minus 90 dBm. Up until now, we've specifically looked at phase noise, but there's more phenomena that can contribute to the degradation in spectral purity. While poor filtering in synthesis, the synthesis process can cause harmonics, the active components used in the amplifier section will cause intermodulation, harmonics, and a degradation of the broadband noise floor. Intermodulation is caused by 2 or more carriers constructively interfering with each other and creates a frequency-related sideband or groups of sidebands. While for every dB increase in the carrier, harmonic will equally increase. For intermodulation, the sidebands increase by a factor of 2 or 3, depending on whether it's a second order or third order product. On the spectrum trace to the left-hand side, we can see the third order harmonics. They're essentially 2 times F minus F2 and 2 times F minus F1. An example of second order intermodulation, by the way, would be the products F2 minus F1 and plus F1. Now moving across to the center, we can see the harmonic performance of the instrument. The carrier at 1 gigahertz, and then at 2 gigahertz we can see the first harmonic and see that that is 60 dB, over 60 dBs down. And finally, the third plot represents our broadband noise floor. So all of these combined will give us the spectral performance of our signal generating device. Advances in DAC technology, or digital to analog converters, have given us components that we can sample at high clock rates. In the case of the Tabor Proteus, the sample clock is 9 gigasamples per second. So in theory, the highest signal we could generate would be 4.5 gigahertz. Although a sine wave at this frequency would not be very well defined, being represented by just a couple of sample points. Now, one thing that we can do, though, is we could reduce the sample rate to 5 gigasamples per second and create a frequency of 500 megahertz. This frequency would consist of now 10 sample points instead of just a couple of sample points. That signal would appear in the first Nyquist zone at 500 megahertz and then in the second Nyquist zone at 4.5 gigahertz. Or to say it another way, sample clock minus the frequency the DAC generated. Depending on the sampling method we've used, the amplitude will vary. In this example, I'm using non-return to zero. If you look at the graph on the right-hand side, I maintain the level until the next sample point. This gives a multiple Nyquist roll-off of a sin x over x characteristics, which you can see in the left-hand plot. Many DACs allow this to be changed. For example, a DAC from Teledyne ETV offers 4 types of sampling: NRZ, RTZ, NRTZ, and RF. We covered non-return to zero and return to zero goes to zero, and then the second two are variations of those two. So let's have a look at a case study of these different types of sampling modes. In this example, we were using the Tabor SE5082 arbitrary waveform generator, and really we wanted to generate a signal at 2.7 gigahertz. This unit has a maximum sample rate of 5 gigasamples per second. So in reality, the highest signal we would generate in the first Nyquist zone would be at about 2.4 gigahertz, and this would consist of a couple of sample points. Plus, as it's only a couple of sample points, the harmonic contact would be quite large. And then one of the applications also required was to shift the signal phase by pi over 2, and that's kind of impossible with just a couple of sample points. Now, if we made the sample clock 3 gigasamples per second, we could create the signal that we want in the second Nyquist zone by generating a 300 megahertz signal. And so it's sample clock minus the fundamental signal, so that gives us 2.7 gigahertz. But then in the center plot, you can see it follows the rules of sin x over x roll-off, and the second Nyquist signal is 20 dBs down from the fundamental. It is true it's made up of more sample points and has better spectral purity, but the amplitude has been severely affected. Now, what we did though was with the DAC, we changed the DAC setting, the sample mode, to the RF mode, which we discussed in the previous slide. This essentially attenuates the fundamental and gives us more power in the second Nyquist zone. So our second Nyquist zone now is only 1 to 2 dBs amplitude difference of the first Nyquist signal that we generated in the top plot. And you can see the fundamental is quite a few dBs down, and the plots to the side show the Nyquist response of each one of the sampling modes. So paying attention to the Nyquist response and the sampling modes is key if you're going to use an instrument in multiple Nyquist zones. When using multiple Nyquist zones, one thing to pay attention to is spectral inversion. In this example, I've set my sample clock to 2.5 gigasamples per second and created two tones with 15 dBs of amplitude difference between them. Both the tones are centered at about 1 gigahertz. Now, if our sample clock's at 2.5 gigasamples per second, then the second Nyquist zone will be 2.5 gigahertz minus 1 gigahertz. And you can see that gives us a center frequency of 1.5 gigahertz, and the spectrum has been inverted. The third Nyquist zone at 3.5 gigahertz is flipped again, so it's back to the original spectral, or it's non-inverted. And then there would be one at 4 gigahertz, i.e. 5 gigasamples minus 1 gigahertz. And the final one I put on the plot is 6 gigahertz, which is essentially 5 gigasamples or gigahertz plus 1 gigahertz. And you can see the spectrum is the regular way around in the 5th Nyquist zone. One thing to look out for, an instrument that you're using multiple Nyquist zones, is the maximum analog bandwidth that's supported. In this unit, the analog bandwidth actually rolls off at 4.5 gigahertz. So the 6 gigahertz signal is a combination of both the sine x over x roll-off and the roll-off of the input filter. Now, an instrument like the Proteus AWG that we've used in a lot of these experiments has an option for a 9 gigahertz filter, allowing the use of multiple Nyquist zones. And in the 5082 that we used in the previous example or on the previous slide, that has a bandwidth that can go up to 14 gigahertz, so you can use it in multiple, again, that you can use that in multiple Nyquist zones. So, if we have analog to digital converters that allow us to create direct to RF signals, then an obvious next step is the ability to embed a modulator into one of those DAC chips. Now, the Proteus arbitrary waveform generator has a complex mixer embedded within its architecture, and earlier on we demonstrated its AM performance in the mixer section of these slides. If you look at the overall architecture of an arbitrary waveform generator at the top of the slide, the internal FPGA routes a required signal from its memory, and in the case of this unit, it's a 16 gigasample memory, to the IQ inputs of the DAC. And the I and Q are mixed with the LO, which is, in this case, implemented by what we call a numerically controlled oscillator, and they have very fine frequency resolution, as it's completely done mathematically. This actually simplifies the creation of signals when we want to shape pulses. If you consider, say, a basic transmon, and in the corner there I have a representative transmon circuit, you would have an AWG mixing with an LO synthesizer to create this specific pulse shape. So it would be a lower frequency AWG, and it'd be a moderate performance local oscillator synthesizer or signal generator creating the local oscillator. The mixer is often an IQ mixer in the pulse shaping example I put on the bottom of the slide. And these need to be balanced and nulled frequently. They're susceptible to temperature changes and they drift over time. So I think what we need to do now is examine the principle of operation of an IQ modulator to be able to understand a bit more about how these operate and how they compare to a digital IQ modulator. In the previous schematic on the last slide, I simplified the mixer to simply a box fed by an NCO and named it the complex mixer. Here we have a more representative version of an actual IQ mixer. It is a combination of an amplitude and a phase modulator. And by mixing different combinations of signals, we can create a vector with a certain amplitude and phase. This is usually represented on a vector diagram, which I've included here. There's two axes, the real and imaginary, or I and Q, or sometimes in electrical terms we call it the in-phase and quadrature components. And so if the I input has a voltage applied to it and Q is set to ground, our vector will consist of only the in-phase component, which would be represented by a horizontal line on the vector diagram. Conversely, if the Q vector has a voltage applied and I is set to ground, we would only have a quadrature vector. So the vector diagram will show a vertical line. All these lines are coming from the center, which is our DC point. If we apply an equal voltage to both inputs, we can create a vector in between the in-phase axis and the real axis, or the quadrature axis, giving us a phase shift of 45 degrees. Not too dissimilar to the unitary circle that's often used, but a different concept, but a similar idea of a rotating vector. By changing the amplitude and phase difference of each input, we can create a multitude of different vectors. And this technique is actually used extensively in digital communications. If we keep the amplitude constant and just keep shifting the phase by pi over 4 or 90 degrees, we could represent the values of, pi over 4 value could be the value 0, 0, and we shift that by 90 degrees, and that would be a 0, 1 value. And then we shift the vector again by another 90 degrees, and that would give us a 1, 0 value. And then the final rotation of another 90 degrees would give us the value of 1, 1. So this is how digital this is how digital communications systems work, and this is where predominantly IQ modulators are used. I've already alluded to that in many cases, analog IQ modulators require calibrating. We actually need to match the phase and amplitude, so we have the correct in-phase and the correct quadrature outputs. So if I take the ADI IQ modulator from earlier, and I place two in-phase 200 megahertz tones generated by 2 channels of my arbitrary waveform generator in the IQ inputs, and then the LO is provided by my lucid signal generator. Looking at the left-hand upper plot, I see that the 2 tones are of different amplitudes, and the carrier feed-through from lucid is 20 dB down from the lower tone. Now, what I can do on the arbitrary waveform generator is adjust the relative phase between the 2 channels and the relative amplitude between the 2 channels, and I can, what we call, balance both the tones so they are same amplitude, and also null the carrier feed-through to minimize it. Now, I spent some time doing this, so that the right-hand plot at the top, you can see, is with the system, with the carrier completely nulled, and the 2 tones are of equal amplitude. Again, this is going to change over time and temperature. The lower section of the slide shows the performance of the digital modulator in the Proteus. It's already balanced and the carrier is nulled, and it doesn't change over temperature. The only drawback, as I explained earlier, is that with a 9 gigasample per second sample rate, the maximum signal in the first Nyquist zone would be 3.6 gigahertz. However, we could use it in the second Nyquist zone. We've covered all our Nyquist theory and multiple Nyquist zones now, so the maximum frequency in the second Nyquist would be 5.4 gigahertz, or 9 gigasamples minus 3.6 gigahertz. Actually, if we set the center frequency of the NCO to 2 gigahertz, then the maximum frequency would be 7 gigahertz, i.e. 9 gigasamples, or 9 gigahertz minus 2 gigahertz. And remember, the spectrum will be inverted. So, to get to a good signal, we actually have to do a combination of digital mixing capability and analog mixing capability, and use a good frequency synthesizer, and then figure out what is a good frequency plan that maximizes the spectral purity while minimizing the nonlinear effects and the effects of other spurious signals. So let's take a look at that next. Optimally creating a spectrally pure signal requires some calculation and some experimentation to ensure the desired frequency modulation meets the control or measurement need. In a commercial instrument, multiple up and down conversions will be used effectively to move the nonlinear or the spurious signals out of band. And a typical multi-stage conversion system is shown in the schematic in the upper portion of the slide. In the lower part of the slide, I have a case study. And it shows an example of a multi-stage up conversion. So my goal was to produce two tones at 6.6 gigahertz with limited intermodulation effects. So first I created a waveform in MATLAB with two tones and centered them around 1035 megahertz. The waveform was 4,096 points in length, and using the fast PCI data transfer of the Proteus, I could quickly upload it, play it out, and change the waveforms very rapidly. I then used the internal IQ modulator tuned to 2.2 gigahertz to modulate these tones. In the example, we're looking at the center slide now. You can see the 2.2 gigahertz carrier feed through, and the two tones space plus or minus 1035 megahertz either side. And they're, looking at the center plot, they're to the left of the plot. On the right of the plot, you can actually see the second Nyquist image of the lower sideband. Well, actually, it's the upper sideband because the spectrum would have been inverted, as we learned about earlier. So I'm going to filter around the upper sideband and then use an analog mixer. And I chose the ADI one because it had a 4 gigahertz of input bandwidth. So with my LO signal being at around 3.3 gigahertz, that had just the right amount of bandwidth. I just use the AM portion in this case. I don't need to use the quadrature part. And mixing those two signals together with the LO setting, I can then get to 6.6 gigahertz. So I now have a feed through at 3.4 gigahertz, which is way lower than my 6.6 gigahertz frequency, and my lower sideband is going to be at 1.2 gigahertz. Given that, I can use a relatively low-cost, commercially available high-pass filter, like a barrel connectorized connector from mini circuits, and ensure that the feed-through and the lower sidebands are fully attenuated if required. And you can see there are no intermodulation products. I do have a couple of spares, 50 dBs down in this example, so there's further work to do on this. I need to determine if there are a multiple of the DAC clocks. That's something else to watch out for. Or are they generated internally by the spectrum analyzer? And what I would do now is I would begin to troubleshoot this by changing the IQ modulator frequency and also the LO frequency, and observing how the spurs behave and how they move around in frequency and amplitude. As we're talking about spectrum analysis or signal analysis, it's a good segue to talk about the subject of analysis. So through this presentation, I've used both an oscilloscope and a spectrum analyzer. And they work differently. A spectrum analyzer sweeps a narrow bandwidth filter through a range of frequencies, and the power displayed on the screen is the measured power in each sweep increment. So as the filter is narrow, the noise power is minimal, allowing me to make measurements with high sensitivity and a wide dynamic range. A variant of a spectrum analyzer is a vector signal analyzer. And this essentially works like a radio receiver. It does not sweep a range of frequencies, but is tuned to a center frequency, and the bandwidth of the receiver filter is digitized and processed. The display could be a direct time domain representation of the acquired signal, or an FFT could be used to show the frequency range. As the filter is wider and the ADC sample rate is faster, the noise and spurious response of this type of architecture is not as good as the spectrum analyzer. But it can analyze signals with time domain behavior, namely modulated signals, very well. An oscilloscope or a digitizer is a broadband device. Its performance is defined by two specifications: its analog bandwidth and its digitizer sample rate. In this example, the input bandwidth is limited to 1 gigahertz by the analog bandwidth, and the sample rate defines the spectral purity of the acquisition, with a sample rate 5 times the analog bandwidth, in this case of 5 gigasamples per second. This allows me to capture whole gigahertz of bandwidth for analysis. However, it has the poorest noise performance of the three due to the wider bandwidths. When I wanted to measure intermodulation, I definitely used the spectrum analyzer because I wanted to get the best possible dynamic range and use the most narrowest filters I could to be able to visualize a signal. But when I wanted to look at a time domain signal or visualize some modulation effects, the vector signal analyzer or the oscilloscope was the best type of instrument to use. So, what if we eliminated the input filter? For the advanced user, this opens up a whole new range of possibilities. And our ability to use the instrument in multiple Nyquist zones now becomes a reality for the digitizer as well as for the analog, for the digital to analog converter. And we call this process, in this case, undersampling. But the theory is exactly the same as what we talked about in the synthesis section and utilization of multiple Nyquist zones. So the Tabor digitizer that's part of the Proteus arbitrary waveform generator, or what we call the arbitrary waveform transceiver, allows this type of operation. And it really does provide a cost-effective method for high-frequency digitization. So let's put it all together. Throughout the presentation, I talked about the Proteus arbitrary waveform generator. It also has a digitizer section, so when it has that, we call it the arbitrary waveform transceiver. So what does that all mean? Well, first of all, let's split it up into 3 operational modes that I put on the block diagram here. So in the turquoise color, that is a state-of-the-art arbitrary waveform generators. 2 or 4 channels with 9 gigasamples per second sampling rates. It has the built-in IQ up converter that we talked about. It has 9 gigahertz of analog bandwidth, so we can use it in multiple Nyquist zones. And it also has a very large memory of 16 gigasamples per second. We just covered the digitizer section, so there is an option on the arbitrary waveform generator called the arbitrary waveform transceiver. And this is the addition of a digitizer and FPGA processing block. So we can sample up to 5.4 gigasamples on a channel, that's with 12 bits, or you can do 2.7 gigasamples on 2 channels. It's got a feedback and control system for conditional waveform generation, and you can customize that in the FPGA. Say you want to do some demodulation, digital filtering, some pulse counting. That can be all programmed in the FPGA block, and you can then control different waveforms. So this kind of closed-loop system is very good for a real-time feedback system. Say you create a pulse, you make a measurement, and you realize, well, that measurement was a bit noisier than I wanted it to be, so I'm going to slightly modify my pulse and do a different pulse. And you want to do very fast, multiple iterations of this. Then this real-time arbitrary waveform transceiver is a key element. And so I put that in the turquoise. Sorry, I said turquoise earlier. I meant blue for the arbitrary waveform generator. And then in the green, I put the real-time signal streaming. So you can stream data to and from, because we put the whole system on a Gen 3 PCIe bus with 8 lanes of capability. And you can stream directly to the FPGA, stream directly from the FPGA and do measurement processing offline and stream back into the system. Say if you want to do some real-time control of some specific voltages and waveforms. So the real-time signal streaming is the third key capability. It's scalable up to hundreds of channels because we put it in the PXI form factor. And also we put it in multiple form factors. So if you want to use an instrument with a screen or just have an instrument sitting on the bench that you connect to your PC, we have the benchtop and the desktop form factors as well as the modular form factors. I also talked about our Lucid signal generator. It goes up to 12 gigahertz. Again, like the Proteus, it comes in multiple form factors, rack, bench, and a brick version. Wide range input power from minus 90 dBm up to 15. it's one of its key contributions in this market is its frequency stability. I pointed out in earlier slides, it's probably got 10 times the stability of other synthesizers that are available. It switches frequency fast. It also has the addition of AM, FM, and pulse modulation within the instrument as well. And one of the key things is because of the pulse modulator, you can effectively turn off the RF output, creating a higher level of isolation between the synthesizer and your experiment. Easily controlled through USB, and for temperature stability, which again links to our aging and frequency stability specs, this is a fan-cooled instrument and can work in very confined environments. So we've covered a lot in the last 50 minutes. We started with some basics or fundamentals, wave behavior, some frequency translation, how that then becomes synthesis. We looked at different methods of synthesis and different the benefits and trade-offs of each one. We looked at modulation, specifically how IQ modulators and how to drive them, how to balance them, how to null them, different types of modulator. We looked at frequency planning, avoiding feed-through, harmonics and spurs to get the best spectral purity where we need it. And then we finally finished on analysis. We looked at different methods of analysis and the different trade-offs in terms of noise. And then we put them all together in the Proteus unit, which is an arbitrary waveform transceiver, and showed you how you can generate waveforms and acquire waveforms and then process them in effectively a real-time closed-loop measurement system.